break.
Right.
So,
Yeah.
Don't make the break, probably.
Yeah. Okay. Fine. We will.
Yeah. Okay. So next speaker is David Carchedi, and he's going to talk about the derived differential geometry and the quantization of gauge field theories.
Thank you very much. It's a pleasure to be here. So this talk will be in two parts. The first part, I'm going to tell you a bit about what derived differential geometry is, and then I'm going to talk about its relationship to the quantization of field theories. So at the heart of derived manifolds is the motivation for them comes out of transversality. So if you have three smooth manifolds and two smooth maps, we say that F is transversal to G. If the images of the tangent spaces at points which have the same image under M together span the tangent space of M. Okay. So an example is if I have the origin thought as a map from point into R, and then I have a smooth function from another manifold, F is transverse to this map if and only if F is a submersion around the origin. Yeah. And as you know, level sets of submersions give you smooth manifolds. And more generally, anytime you have transverse maps, the fibered product exists as a closed submanifold of the product. In particular, I get the zero set. So you can say, okay, well, what about when I don't have transversality? Well, all bets are off. It fails drastically. Any closed subset of any manifold is the zero set of a smooth function. Yeah. So you could get anything, any kind of closed subset of any manifold as such a pullback, but the pullback doesn't really exist because it's not a manifold. Okay. So that's an issue. So the main idea is derived manifolds are meant to fix this problem. So I'm not telling you what they are yet, but I will. The idea is that you can form pullbacks of derived manifolds, any pullbacks you want. All manifolds are derived manifolds. And when you have transversality, you get the normal answer. Okay. And a general derived manifold is built by iteratively performing pullbacks and retracts. Okay. But there's a price to pay. Derived manifolds form an infinity category rather than a category. So if you don't know what that means, it basically means that, oh, say I have two smooth maps between derived manifolds. I could, oh, yeah, use my pointer. I could talk about an equivalence between those smooth maps. If I have two equivalences, I can talk about an equivalence between those equivalences. And then I can keep going all the way up. So in other words, we have an infinity groupoid of maps. You can think about it as a space where the points are the actual maps, the paths are the equivalences, the path homotopies are the equivalences between the equivalences, etc. Okay. So lack of transversality, it causes some issues. One way to construct many moduli spaces is, oh yeah, one way to, yeah, absolutely, I forgot, thank you. One way to construct many moduli spaces is to consider the zero sets of a section of a vector bundle. So, and this can be very singular when it doesn't meet this, the zero section transversely, right? So if I have a section, I try to look at zeros, it can be very singular. And some examples I have in mind is like moduli spaces of incitons or J homomorphic curves or set of solutions to Euler-Lagrange equations. Though these are infinite dimensional, but I will be going to infinite dimensions later in the talk, so I'm allowed to cheat and say that, okay? All right, so there is a model for this intersection as a DG manifold, even when you don't have transversality, okay? We saw this in Mathieu's talk. Just one remark is DG manifolds for us, we won't be taking formal power series, we'll just be taking polynomials. Otherwise, it's the same. What?
The degrees are only non-positive.
Well, and not a general DG manifold, but the ones I'm caring about, yes. Yeah. Yes. So, I mean, you can talk about my definition of DG manifold allows all the degrees, but I'll be concentrating on the ones which are a non-positive degree. Okay. Oh, and forgive me, this was supposed to be a -1, which I think I fixed on all the other slides. So you just take the vector bundle, you shift the parity, and then you use insertion of the section as an operator. So the sheaf of functions on this, well, first of all, it's graded manifold. It has underlying manifold, the original manifold. And the structure sheaf in degree -n is the nth wedge power of the dual sections of that. And then insertion of the section is your cohomological vector field. So why? Why is this a good model? Like what is this doing? So if you look in local coordinates, say I have sigma i's are the coefficients of your section in a basis, then what does your structure sheaf look like? It looks like smooth functions on that open adjoined k variables in degree -1, where k is the rank of your vector bundle. And then the differential is the causal differential. So you have a causal complex, right, associated to the ideal generated by these smooth functions. Okay. And as a consequence, we have a couple of things. One is if I do have transversality, then this DG manifold is equivalent to the actual intersection. In this sense, they have a quasi-isomorphism, okay, between their global sections, if you will. And the second is the cohomology is a cyclic away from the zeros of that section. So if I take any neighborhood at all of the zeros and I restrict the structure sheaf there, that DG manifold is equivalent. Okay, so all the information is contained at where the real intersection is. So this is like a kind of idea of why this might be a good idea, but I have to make sure that it's actually computes the right thing. And what do I mean by that? Yeah. So in order to talk about derived manifolds, we need to talk about something called C-infinity rings. And the reason, and it may not, I mean, it's kind of like surprising that C-infinity rings are intimately connected to derived manifold. You can't avoid it. Okay. What is a C-infinity ring? It's just a commutative R algebra, but you have additional structure. Anytime I have a smooth map, say from Rn to R, I get an area operation on that ring, and they're compatible in a suitable way. And I'll make that precise, right, by representing it as a functor in a moment. So the prototypical example is just smooth functions on a manifold. Okay, if I have a smooth map from Rn to R, I can just put my other smooth functions inside of that function, and I get a new one. So that's pretty easy. That's an area operation. Okay. Now, you can also do this for supermanifolds. We are talking about supergeometry in this conference, so why not mention this? This is due myself in Rodenberg. And then you have, when I have a smooth map from R and M, I get a map from this n copies of the even functions, m copies of the odd functions. It goes into the evens, and I go into the odds for every map into the odd line. Okay. Is this okay? Okay. So the prototypical example is just smooth functions on a supermanifold. Okay, so that's kind of the motivation. All right, so let's make this formal. So what you do is let C-infinity be the full subcategory of manifolds on all those of the form Rn for some n, including 0. Okay, so the Euclidean manifolds. A C-infinity ring is a finite product preserving functor from that category to set. So you may say, like, well, it's a functor. How is it a ring, right? Like, it's the category of Euclidean manifolds, Rn's. Yeah. So you just take only R to the n for different n's and the smooth maps between them, and that's C-infinity. That's the category. I apologize, that's not readable. It's like super bright on my screen, and it's not here. So, okay, so why is this a ring? Well, the real line is a ring object in manifolds, right? Addition and multiplication, those are smooth maps. And because the diagram expressing the fact that it's a ring just uses finite products, you get a ring structure on the value on R, okay? So indeed, if I just look at applying A to this, I get a binary operation, similar with multiplication, and then they're forced to be compatible and gives you a ring structure. And so that's how you formalize what a C-infinity ring is, okay? Okay, and
you're saying that you can apply smooth functions with many arguments to elements of the algebra.
Yeah, yeah. Mm-hmm.
So besides ordinary ring operations like addition multiplication, you can substitute elements of the algebra into smooth functions.
Absolutely, yeah, because like a ring is something where you can do that with polynomials, a C-infinity ring is something we can do that with smooth functions.
Yeah.
And that makes smooth functions on Rn the free C-infinity algebra on n variables.
Yes, yes.
Yeah.
Which people normally think.
Yeah, yeah. So this is a way of making that precise. So we have a category of C-infinity rings, and there's a tensor product. It's the coproduct, and it has the condition that if I take the tensor product of smooth functions on a manifold with another, I get smooth functions on the product. So recall, if I take smooth functions on M and I just tensor over R, this is definitely not true, right? This is not equal to smooth functions on M cross N. Yeah. So, but this works if I take the C-infinity tensor product. So that's cool. And another thing is the functor from manifolds to the opposite category of C-infinity rings is just take smooth functions. It's fully faithful. So it embeds manifolds in there, and it preserves transverse pullbacks. So this is where it's starting to connect with derived geometry, right? Those are the pullbacks that we want to keep, right? And those ones are preserved. Okay. Yes, I mentioned you can do all of this with supermanifolds as well. You replace Euclidean manifolds with Euclidean supermanifolds. And then everything else is the same. Okay, so we want to go derived. We have to do some kind of homotopical algebra. Okay, so one way of talking about homotopical C-infinity rings is to talk about DG C-infinity algebras. And that's just a commutative algebra which has additional structure of a C-infinity ring on the degree 0 part. Okay, this definition was due myself in Roidenberg, and we so first of all, the prototypical example: smooth functions on a DG manifold. So it's just kind of like the way we're going, right? You've got smooth functions on the manifold, smooth functions on a supermanifold, smooth functions on a DG manifold, kind of guiding you about what kind of functions you should be using. Yeah. And as these are homotopical, there's a nice model category. We have one for unbounded case as well, but as we're doing derived geometry, we're going to concentrate on those in non-positive degree. Okay, so there's a nice model structure there, but there's other things you could think about might be a homotopical C-infinity ring, like simplicial C-infinity rings. Yeah, so Dima wrote down a C-infinity Dodkan correspondence, which is Euclidean equivalent between these model structures, and Joost Nauten in his thesis wrote an infinity categorical proof that these give you the same infinity category. So anytime you have a model category, if you just take the weak equivalences and you invert them up to homotopy, that gives you an infinity category. Yeah, like the simplicial mapping spaces become your infinity groupoids. Yeah. And yet another thing you can do is you can talk about C-infinity ring objects in the infinity category spaces. Okay, whatever that means, but I'll tell you in a moment. Okay, but that's also equivalent just due to general results in algebraic theories. So this comes from Julie Bergner and independently by Lurie, that this always works. So what is an C-infinity ring object in the infinity category spaces? So the infinity category spaces is just, you just take topological spaces and you take their mapping spaces as your maps. Okay, it's representing infinity groupoids. That's the idea, right? And a C-infinity ring object is just a finite product preserving functor from C-infinity, but now into spaces. That means it preserves a product up to homotopy, right? But I mean, as written in the language of infinity categories, it's just a finite product preserving functor. And I can do that for any infinity category I want. It doesn't have to be spaces. Anything I want. I can just talk about a C-infinity ring object. If I took just the category of sets, I get C-infinity rings. If I take, say, sheaves on a manifold, I get sheaves of C-infinity rings, etc. Okay. All right. So, okay, and this all goes for super stuff as well. There's no issue there. Okay, so let me switch gears for a second, go back to derived manifolds, and then all of a sudden C-infinity rings are going to appear. So that's kind of surprising. So first of all, whatever derived manifolds are, they better include manifolds. Yeah. So I should have a fully faithful functor from manifold to derived manifolds. That's certainly one of the requirements. Now, I want this to preserve the transverse pullbacks. You can't read this, and terminal object. Okay, that's a natural requirement. I mean, otherwise, what are we doing? And I want to be able to construct iterative pullbacks. So I should have finite limits. So that just means I'm going to have pullbacks, arbitrary pullbacks, and the terminal object, yeah, and idempotent complete, so I can split idempotents. Okay, this is just for the retract part, right? So you can say derived manifolds is an infinity category universal with respect to these requirements. What does that mean? You can say, well, anytime I have any other infinity category which has finite limits, and I can split idempotents, and I have a functor from manifolds to that infinity category which preserves the transverse pullback and the terminal object, that it extends uniquely to a functor from derived manifolds to C which preserves all finite limits. That's why they're kind of freely generated or freely constructed out of manifolds using those operations. That's a way of making sense of that. Okay, so by abstract nonsense, there exists such an infinity category, but that's not really useful if you can't work with it, right? You'd have to have a nice description of it. Okay, so okay, oops, what just happened? I went flying somewhere else, backwards in time. Okay. Okay, so there exists such an infinity category, but what is it? Well, it turns out, and this is kind of surprising, that there's an alternative characterization of this same universal property. So one way of saying that is, so first of all, what this universal property is about functors out of derived manifolds which preserve finite limits, yeah? The theorem of myself and Pella Steffens is that finite limit preserving functors from derived manifolds into any such infinity category C is also equivalent to C infinity ring objects. So as soon as I have a C infinity ring object, that tells me where all the Rn's go. And then it tells me, because it has to preserve the retracts and the pullbacks, I can then construct the rest of my manifolds. Because Whitney's embedding theorem, I can embed into an Rn, I can use tubular neighborhoods, and then it tells me where all the manifolds go, and then tells me where all the derived manifolds go. Okay?
There's a role of free resolution.
Free resolution? What do you mean?
Like for algebra, so because the algebra you set up, the algebra function Rn,
yeah,
there's a role of free algebra.
Yes.
So if you embed the manifold, that means.
Oh, okay. Yeah. Yeah. It's. Yeah. That's exactly. Yeah, exactly. That's kind of the idea. But then you have to do retracts, unfortunately. But yeah. So now this is the algebras for any algebraic theory. There's always a gadget which does this. That has this universal property. It's just the opposite of the finitely presented algebras. So the corollary is that one model for derived manifolds is just the opposite category of homotopically finitely presented DGC infinity rings. Okay, so this just follows just by category theory at this point, and that gives you an actual concrete model, and then you can talk about. So basically, that's the same as just affine derived C infinity schemes of finite type. So the upshot is derived manifolds are just derived schemes in the C infinity world. They're finite type. And then derived different geometry is just derived algebraic geometry over C infinity rings. Okay, and we have no choice in that matter. We're forced. Okay, so that's what I want to tell you about derived manifolds. Okay, so you can also do this for supermanifolds. Everything works. Okay, and now I want to go to part 2 of my talk. Okay, and I'm going to talk about field theories. Okay, so I'm going to jump out of this program and go into this program, which is where I have a more kind of interactive presentation here. So let's talk about classical field theory. Okay, what are the ingredients? Well, you have a manifold, which you can think about as space-time. You have a configuration bundle, and sections of that bundle are the space of fields. Okay, so what are the other ingredients? You have some action functional. So you have something, a Lagrangian density, so it's something you can integrate over space-time, which is associated to each field. And if this actually converges to a number, that would be the action functional's value on the field. Physicists don't really even care if it converges or not, right? So, but in principle, if these were all numbers, you want to minimize these functions because these are like the potential energy, and that tells you the classical. Whoops. Don't do that. Undo. Okay. I will fix that and continue. All right. So classical dynamics, it tells you that the physical fields minimize this. So the variational derivative of the action should be 0, which really, this is just thinking about the Lagrangian density. So you can just say the variation of the Lagrangian density is 0. Okay. All right. So that's classical field theory in a nutshell. Okay. What about when you go to quantum? Okay. So we'll just take an H bar and it'll move us over and we'll talk about quantum field theory. Okay. So that's all you do. You just take H bar. I'm done. All right. No. So you have some algebra of quantum observable. So these are the things that the measurements you can make on your fields. Okay. So it's some algebra. You can think about these as some functions on the space of fields. Okay. And you want to compute some expectation value of such an operator. And what you do is you look at the value of the operator on a field. You weight it by some exponentiation of the action with an H bar parameter on the bottom here. And you integrate over all the fields. And then you just divide this by doing the same thing for the identity. And here I have this d phi, which is some measure on the space of fields, but this is a lie, right? I mean, you can't do this. This is, I mean, as far as actually writing it as integral, there is not a measure on these except for in the case of the Wiener measure. So you can do it for quantum mechanics, but not beyond that. But this is the philosophy, right? And there's ways to get numbers out of this still using Feynman diagrams. But this is the idea, okay? And this does make sense in one baby case, which is space-time is a point, okay? So let's do the baby case because it will show us why derived geometry is important. So let's go over here. All right. So the warm-up situation is space-time is a point. I then have my configuration bundle is assume it's n-dimensional, compact, and oriented, so there's no problems. Then the sections are the same as the bundle because we're over a point. Okay. And now integration over a point isn't anything, right? So the action function is just a smooth function on the space of fields. So Euler-Grounds equations just say that the one form ds is 0, right? So we're looking at the zeros of that section. Okay. All right. So we need something to play the role of the measure on the fields. So let's just fix a nowhere vanishing top form. Okay. So if I have a nowhere vanishing top form, I can use contraction with it. And it gives me an isomorphism between multi-vector fields, say of degree I and n-i forms just by contracting. Yeah. So this gives you an isomorphism. I have a cochain complex here. So I get a nice chain complex on my multi-vector fields. And the Derived differential, it becomes the divergence operator, right? That's how you define divergence. Yeah. Now, we don't want to integrate against that measure. We want to integrate against that measure weighted by the action function. Yeah. So, but there's no problem here. We can just take this function, which is a complex function. If we fix h to be some actual number and multiply it by mu, and the same story works. So let's see what happens. So let's take a smooth function. It should be with values in c. And I want to compute this. I want to compute the integral of x against this weighted measure divided by this partition function. Okay. All right. So I take smooth functions on f with values in c, and I can map it to the 0th cohomology because this is of the chain complex I have on multi-vector fields. Yeah. And well, that's the same as the nth cohomology of f with values in c. And the isomorphism is just given by multiplication with this weighted measure because there's nowhere vanishing. And then integration gives us a complex number. Okay. All right. So because we have a nice isomorphism here, right? So therefore, we can define are, there's going to be a complex number which multiplies this class in cohomology to give you this class. Yeah. So then that tells you what the expectation value is. Yes.
Why do you need these classes now?
Well, this is, what if I can't integrate? I can still construct a cohomology and I get these classes. So that's the idea, right? So I'm trying to do something which I started when I have a way to integrate and then mimic it when I don't have a way to integrate. Okay. All right. So let's see what else we have from this. Okay. So let's, first of all, it lives in the zeroth cohomology of the complex of multi-vector fields with the divergence operator as your differential. Okay. Yes. Exactly. Yeah. It's a one-dimensional because it's isomorphic to C. Yes, but it's okay. Sorry. It's zero homology. Yeah. Sorry. Yeah. Zero. I put it zero. It just jumped. It shouldn't have. It's down. It's really down there. Okay. Zeroth homology. Sorry. Absolutely. That's all it is. But I just wanted to point out that this is a way of. Yeah. Exactly. Everything's finite right now. Completely finite right now. Everything's finite. Well, yeah, X is a function, so it doesn't have any dimension. But M is a point. F is n-dimensional because space-time's a point, and compact and oriented. So okay, everything's a manifold right now. Yeah, everything's a manifold. I have space-time as a point, and my configuration bundle is a compact oriented manifold, and that's all we have. Yeah, well, no, not vector bundle, but well, no, it's not a vector bundle. It's a fiber bundle. Yeah. Yes, just so I can integrate. Yeah. Yeah, no fermions right now. Okay, so like you're overthinking. Don't overthink, right? Let me overthink. That's my job. Okay. So here's a simple calculation you can get from Cartan's magic formula: is that what's the divergence operator associated with this weighted measure? If I multiply by IH bar, it turned out to be insertion of ds plus IH bar of the divergence operator of the original measure. Okay, so you can just do this calculation. I invite you to try. It's not too hard. And so this gives you, this is a differential on your multi-vector fields you get. And what happens when H bar goes to 0 is that this survives. So like the semi-classical limit, we have still a differential. What do we get? We get this chain complex of multi-vector fields with insertion. That's also a co-chain complex if I just change the gradient to be in non-positive degrees. And this is smooth functions on this DG manifold, which is supposed to give a model for the derived zero set of this section. So it's the derived space of solutions to the Euler-Lagrange equations. It's popping up out of nowhere, so to say. So what? What operator?
It's from the new H bar.
Yeah, it comes from the mu H bar, which is mu times e to the I over H bar S. And then there's a calculation. If you calculate what the divergence operator of that measure is compared to the original divergence operator, the difference is insertion of that section. Yeah, that comes from just like some calculation. Yeah. No, there's action on both sides, and mu h is hidden. And mu h is just as you take the volume form and you multiply it by e to the I over h bar times the action function. No, it's clear. Okay. So we discovered this derived critical locus, so it's a dry space of solutions to the classical field equations. Okay, so that's nice. Okay, now I turned h bar to 0, but I mean I shouldn't do that. I want to be quantum. what happens when I don't, right? So when h bar is not 0, I guess I should technically -1 shift it, but it's
But what you get now in this h bar to 0 limit, you average the function x over the 0 locus of s, right?
when you set h bar to 0, it's
Of this expectation value.
yeah, you're just taking the average of the function. Yeah.
Over the 0 locus.
Yeah, I guess. Yeah. I have to think, but yeah, I mean, I'm not, all I'm saying is I get this complex h bar is my formal parameter that makes it quantum, and I just set to 0. So that's all I'm thinking about right now. You're overthinking. Yeah.
How about you take the value at the point ds equals to 0? It's not s equals 0, it's ds equals 0.
Yeah. Oh, did you say s equals 0? Sorry, ds is 0. Yeah.
This is exactly my question. When you h bar goes to 0, you only IDS left. You don't see this is the second part of the operator, no?
Right. We only have IDS left
But
when,
then this is
when
why
h
this
bar is
still
0. But when h bar is not 0, I have more. I have a divergence operator. Yeah. So when h bar is not 0, let's see what structure we have. Well, this part doesn't really matter. I still have it. I have the Sheldon bracket. Yeah. And I have a Poisson bivector of degree 1. So I guess that's actually called a -1 shifted, but ignore that. That's just because it matched with symplectic. This divergence operator is a derivation in respect to the Sheldon bracket, but not with respect to the wedge product. The failure is measured by the Sheldon bracket. Okay, so we have this. So algebras which satisfy these property, like with h bar being a formal parameter, so like living over the formal disk, these are called BD algebras, balanced and Drinfeld algebras. It's basically BV algebras, but I mean letting h bar be formal. And moreover, this algebra, it's a deformation of the algebra of functions on the derived space of solutions. So this kind of guides us of like what we should do in general, yeah, when we're not in finite dimensions. Okay. Questions so far, like before I like really go flying.
Yeah, but then you lost this the critical locus looks like. No?
Why?
I mean, you
No,
don't
I didn't.
pure this one. the
How did I
operator
lose
there.
it?
With the div, that's
This divergence of mu h bar. Mu h
Oh.
bar is here. I'll write this here for you, just so you see it. Mu h bar is e to the I over h bar s times mu. It has the action functional in it. Yeah.
But the complex is still isomorphic to the rough complex
Yes.
without anything.
Yes. But I mean, we don't have that. We don't have that in infinite dimensions. If I have fields infinite dimensions, I can't use the Ram complex anymore, right? It keeps going, right? So, but
Limit h1 to 0
Well,
is
you don't have this either in the infinite case.
no, you do when you quantize.
Well, it's well.
Not
Yes.
integrate, not
Model of the existence of the mean or final integral. So it's just you're coming back.
Well, no. Look, now I said now the meaning in the cohomology class, and now we just have to find a nice thing to take cohomology of.
But is the limit of this h bar smooth in h bar to 0?
Well, yeah. Because when you, if I did I h bar times it. So I h bar times the divergence mu h bar. That's how I get the limit to exist. Okay.
But this expectation value x of h bar sub h bar. So this is for any x. This is smooth for x h bar to 0.
Well, I don't know what you're actually. I'm just taking the limit of this,
Yeah. But I mean, this expectation value.
the expectation value, e to the minus I over h bar, and then so that's gonna go. Yeah, I mean, yeah. Well, yeah. So I mean, if you had nice regularity of the function, then it's gonna like localize to the critical locus.
Then it's
So,
smooth.
yeah.
It's continuous.
Then it's just, yeah, I mean, those are gonna, yeah, then it will be, I think. I don't want to make a statement without thinking, but yeah. Okay, so what do we do when space-time is not a point? Okay, because in real life, the space-time I live in isn't a point. So what can we do? So let's go and do this for real. Okay, so I have my configuration bundle. My fields are the sections of this bundle, so it's infinite dimensional. I have my action functional, and I have the Lagrangian density is going to be a function on fields with values and densities. It actually only depends on the infinite jet of it, but I'm just simplifying it. I can think about it as a function like this. Okay. So what is the derived space of solutions to the Euler-Lagrange equations? What would that be? So first of all, if I just take L as a function and I take DL and take the cotangent bundle and try to take the zero set of that, I'm going to get something terrible. It's not going to look like anything useful. It's not going to match up with physics. And there's a reason for that. We shouldn't be thinking about it as a real valued function. Well, I shouldn't say L, it should say X, right? First of all, it may not even give me, if M is not compact, it may not even be a number. And second of all, you should really think about it as a function into densities, okay? So everything from here is joint work with Owen Gwilliam. So we want to construct something which we call the variational cotangent bundle. And it satisfies the analogy is it is to the ordinary tangent bundle as smooth functions with values in R are to smooth functions with values in densities. Okay, that's the idea, but I will give you an actual definition. But it's constructed in such a way that also the variation of a Lagrangian density naturally gives you a section of this bundle. And then you can define the space of solutions to be the derived intersection of this section with the zero section. But these are infinite dimensional. So like, wait a minute, like how can I do that, right? But I'll get there, okay? So if I pretend I can do that, then this tells you what to do, right? At least I have a vector bundle and I have a section. So, and that will give me my space of solutions. But before I go derived, there's one more issue, because I often have redundant information measured by a gauge group, the group of gauge symmetries of my field theory. So I have some gauge group, which is typically also infinite dimensional, acting on the space of fields. And two fields are related by that group if they describe the same physical system. Think about electrodynamics, and you can choose potentials that aren't the same, but describe the same theory. Yeah. So the main example will be looking at connections of the principal bundle as our space of fields. So I have some principal bundle. I'll look at the affine bundle of connections. If it's a trivial bundle, this is just Lie algebra valued. Well, it's sections of a Lie algebra valued one forms. Yeah, connection forms. And well, the gauge group is sections of the adjoint bundle. The big adjoint bundle is a bundle of Lie groups. If you don't know what that is, just think about the trivial case and just smooth functions as values in the group. Okay. So we're going to construct the derived space solutions in two steps. First of all, we're going to take the stacky quotient of the fields by the group action, because it may not be free. Okay. And then we're going to look at the variational cotangent bundle of the stacky quotient and then take the derived clinical locus of the action there. Okay.
What does that mean?
I'm going to tell you. I'm going to tell you. These are good questions. Like, I mean, I'm not going to say I'm done, right? I owe you an explanation, right? And I'm going to give it to you. So, but let me just remark that this variational cotangent bundle with a stacky quotient, it actually already has the data of the ghost fields, it turns out. Because remember, ghost fields from, like, say, BRST are responsible for resolving the action, right? So they don't have anything to do with the action functional, they have just to do with the action of the gauge group. So that's part of the data of this variational cotangent bundle. So let me tell you how this works. And then first of all, you want me to be precise, let's do a formal setup, okay? I just take sheaves on derived manifolds with values and spaces, and I work there, okay? So, but for technical reasons, I just thicken it up a little bit to allow some infinitesimal objects, just for make life easy. So I represent the fields by their functor of points, okay? So the functor of points on some derived manifold would be, I'd have so if D is a derived manifold, I have a D family of sections of this bundle. So it's just a map from D cross M to E, which makes this commute, okay? Now, this is actually a space because maps from a derived manifold to a manifold forms a space.
What is the epsilon?
It's the configuration bundle. It's a configuration bundle. Sections of this is F. Sections of this is F. This is a bundle. And now I'm just looking at deparameterized sections. And that tells you how to look at its function of points. Okay. And you say, well, is this a reasonable thing to do? I mean, like, can I think I'm going to actually capture the infinite dimensionality? And well, there's this nice remark that, and if it don't go derived, just go to, and just take sheaves of sets. All infinite dimensional manifolds are recoverable from their function of points on finite dimensional manifolds, like Carchedi manifolds, or even like ones that are just locally convex. I mean, they land actually in different logical spaces even. So we have hope that this should be good enough for our purposes from the derived world too. Okay, why are you shaking your head no? You can reconstruct the infinite dimensional manifold by knowing all smooth maps into it by finite dimensional manifolds.
Oh, no, if I take L1 and L2 of smooth functions, L1, no, I take smooth functions on R, L2 functions on R, they have the same smooth map from R and to them.
What? Let's talk later, because I mean, like, we can discuss. But I mean, this is the theorem, okay? So like Carchedi manifolds in particular will embed in there. Okay, so now at least I can talk about the fields as some object in this topos, and it's really infinite dimensional manifold. So that's like, it's just a function of points of it. But at least when I haven't taken the stacky quotient, yeah? So first of all, the tangent bundle of this object, you can prove, like the tangent bundle in the sense of like just mimicking derived algebraic geometry with these C infinity rings. It's the space of sections over M of the vertical tangent bundle of the configuration bundle. So the vertical configuration bundle is over the configuration bundle, and this is over M. And we're looking at sections like that. Yeah, that space of sections is the total space of your tangent bundle. And so in particular, the tangent space at a field is sections of the pullback via that field of the vertical tangent bundle, which is what you expect even when you work with infinite dimensional manifolds, those kind of your local models. Yeah, except for Peng doesn't think so. Shaking your head. Okay, so I mean, we can talk, but like I mean, you can formulate what's a tangent bundle that's like maps from the formal disk in. And that's one way of constructing it. Okay, so it's just done synthetically. And so what you do is you construct the variational cotangent bundle. You take the relative Serre dual. Okay, so what is that? I just take the vertical cotangent bundle, I pull back the density bundle of M, and I tensor, and I take sections of that, and that's my variational cotangent bundle. Okay, so that satisfies the properties that I want. This is like where the field should, like the antifields should live. No, sorry, antifields. Well, yeah, so yeah, exactly, where the antifields should live. Okay, fine. Is that okay? Yes, kind of. So what about when I have a gauge group? Well, then you actually have a two-vector bundle. So the tangent complex, the tangent space is, the fiber is a chain complex. So it's in degree -1, it's the Lie algebra of the gauge group, and degree 0, it's a tangent space, and then we have the infinitesimal action as your differential. Okay, so that's just a simple calculation. And well, first of all, and this is probably, I mean, this is proven also in like, in the case of using infinite dimensional manifolds, but in this setup, I can prove also that if I take this, this standard case of like the affine connections, if you work out what this is, you get sections of the little adjoint bundle, and then we have a map to, so the tangent space is the adjoint bundle, sections of that tensor the cotangent bundle, it turns out. And then this map is nothing but the covariant derivative on the associated bundle, right? The adjoint bundle is an associated bundle to the principal bundle. So if I have a connection, I have an associated covariant derivative on all associated bundles I get from the principal bundle, and that's what this turns out to be when you calculate it, okay? Yes.
So when you say formation of the group, like, think that only the algebra plays a role.
Well, at the tangent space only sees a Lie algebra. Yeah. Just, I mean, that's not like surprising, right? It's infinitesimal action. Yeah. So, okay. So what do we do? Well, basically what we want to do is, so first of all, this is a differential operator. You can prove it's always differential operator here. It definitely is, but it actually always is in this setup. It turns out you can prove it. Okay, and you basically want to construct a new bundle where I want to take the formal adjoint, but I'm going to shift it up. So it's like the dual, but like in the sense of differential operators. Okay, fiber-wise. So a way to do that is you can interpret differential operators in terms of like infinite jet comonad or using Derived stack. So there's some technical details, but you can do this. You can make sense of this. And so what you do is you use Verdier duality for D modules. Okay, like a relative version of Verdier duality. So if I have a differential operator between vector bundles, I can take the Verdier dual between the tensors with the densities after I take the dual. Yeah. And this intertwines Serre duality. Yeah. So if I have an actual linear map. So this is a construction you can do, but really all I'm trying to do is just construct a new vector bundle where the fibers are just a formal adjoint. Okay. It's like the chain complexes. I take the Serre dual, right? And then like I did before, and now I just like, what do I do? The differential, I take the formal adjoint. Okay. I just need to.
But your space is F calligraphical.
Yeah.
What is this? I mean, you don't like this
F,
easy Derived space.
F is just sections of my configuration bundle. So it's infinite dimensional manifold.
So for example, if it's
Affine connections. Yep.
and then you quotient by,
Well, if I do quotient G, that means that, yeah, I take the quotient stack.
that's meaning what? I mean, do you take into account things like reproducible connections? So, I mean, whatever physicists struggles with quotient.
I don't do, I just literally take the quotient as a stack. Like, I mean, you just take the action groupoid and you just take the associated stack. That's it. So, I mean, I don't know what those are. We should talk because like maybe there's something that needs to be rectified, but I seem to get the same answers as the physicists anyways, as what I'll get there. So I think what I'm doing is the right thing.
Single part you get it, but I'm trying to understand what's complicated. Maybe not really taking the quotient for the whole problem.
Yeah, I'm not taking the actual quotient, I'm taking the stacky quotient. If that, so it's, I can explain to you what that means later if you want. But it's like.
May I make a comment? For the slides which relate maybe Abedo's question and the Maxim's question for the tangent bundle of the quotient stack, you say G F over G, something like this.
Yes.
I think maybe this is a good point to make advertisement for tomorrow's kilo section. That's exactly the transformationally algebraic of he's taking transformationally algebraic of the gauge group acts on this F.
Yeah.
And that's just the anchor map.
Yeah, it's the anchor map. Yeah.
And that is the basically, if you look at the stack, that's tangent complex of the stack.
Yeah, that's exactly how I drive
I
that.
think that's exactly like a Keelios with this algebraic point of view. That's the anchor map of.
Thank you, Ping. That's exactly the way that I prove it.
Marvelous.
No, that's great because I think it also elucidates why this is true. So thank you. Okay. So anyways, I use this notion of Verdier duality. It takes a lot of care to do this, but I construct a relative, so a fiber-wise Verdier dual of this two vector bundle. Okay. So I managed to construct this global object where the fibers, I have just the dual complex in the sense of D modules. Okay. And then our variation of Lagrangian density is a section. And these are now all real actual objects. These aren't heuristic. I'm not waving my hands. These are real things I can talk about. These are living in that infinity topos. This is like the stacky quotient of the functor points of the sections. And this is, well, some construction which you can do, like, and it's rigorous. And now we're in the derived setting. So anytime I take a pullback, it's a derived pullback. So I just take the derived pullback, or in this case, right, as equalizer, I equalize the zeros and this variation, and I get the derived critical locus. So some infinite dimensional derived differentiable stack. Okay, but it's an actual object, and it is infinite dimensional. But with a little bit of work, you can show that it's still nicely behaved with respect to deformation theory. So you can do perturbation theory on it. So we can connect back to perturbative quantum field theory. That's important. So if in case you want to know what an infinite derived stack looks like, there you go. That's what it looks like. Okay. So suppose I take a solution to the Euler-Lagrange equations, a classical solution. That'd be an actual point in this stack. And I can take the formal neighborhood. The formal neighborhood is encoded by an L-infinity algebra. This is, due to Lurie. Yeah. So formal multiply problems and L-infinity algebras are the same. And this whole construction, the space of solutions, it glues together over space-time and open. So you get a sheaf. So you get a sheaf of L-infinity algebras. And the underlying cochain complex of this L-infinity algebra is nothing but, well, a shift of the tangent space. Okay. So this is just a general setup. This is usually done for just like derived schemes, finite dimensional, but it turned out to work here. I proved that all the stuff you need to make it work works. And you can calculate the tangent spaces in like physically meaningful examples. Like if you do 3D Chern-Simons, you calculate what is a tangent complex, you get differential forms and M with values in the adjoint bundle. And the differential is just the covariant derivative operator, which squares to 0 because the curvature is 0. The classical solutions to Chern-Simons are connections with curvature 0, and you just shift. And this just comes out. You calculate it and it comes right out. So it's pretty nice. 2. Yeah. That's just what, like, yeah, it's just what comes out. Yeah, it's like starts at -2 and keeps, yeah. And for Yang-Mills, you get something very similar. So you in degree 0, you have the same. You have sections of the adjoint bundle. Then on degree -1, I have one form to values in the adjoint bundle. And then I jump to n-1 by taking the Hodge star of D with itself. And then I continue. And that's what you get. Okay. So these complexes are exactly what comes out from BV quantization. So this is like really cool. Right? It's just reproduced by this like for free. Okay. All right. So what can you do? Well, if you take Chevalier-Algenberg cochains of this L-infinity algebra, it gives you a Poisson algebra with a bracket in degree 1, and it's actually also a factorization algebra over the manifold. And you can ask, well, can I quantize this? So this is basically this plays the role of smooth functions on your classical locus, except for it's a formal neighborhood thereof. So well, what you should do is you should just lift this to a factorization algebra with values in BD algebras, just like we did before when you turned when H bar is not 0, the divergence operator gives it the structure of a BD algebra. So we're just finding a BV Laplacian, okay, operator, so there's comotal obstructions to doing this, but it's shown that you can do this for like all of the physical examples that people care about. But that's like over a single point. So I fix some classical solution. And I don't need this global object to do that, right? This is all just a formal neighborhood. So why do I have this global object, right? Well, I can use this for families of solutions when I have the global object. Any derived stack mapping in, instead of getting a sheaf of L-infinity algebras, I get a sheaf of L-infinity algebroids. And you can still take Chevalier-Algenberg cochains, and you can ask the same question. I get a factorization algebra with values in P0 algebra still, but now it's coming from a sheaf of L-infinity algebroids over whatever the stack I use to parameterize my solutions is. I mean, I could just take R and have like a just nice family of solutions. But why do I say a stack? Well, what about I just take the identity map? Yeah. If I take the identity map, then I'm looking at Chevalier-Algenberg cochains of just the L-infinity algebra structure on the tangent complex. So you could ask, is there a global BV quantization of this? Yeah. And so anyways, what I want to do next like not next in the talk, I'm like basically done here, but next in my research, once I finish filling all the, like this, I'm still tweaking some of the demodel details, but like, I mean, it works, but I want to make it cleaner, okay? Is I want to like identify the cohomological obstructions to global BV quantization, and then work this out in some examples where I can relate it to manifold invariance, right? Like if I take like the A model, right? Like I can get, because of this, I can get contributions by incitons because I have all of the solutions, yeah? So you have hope to recover interesting manifold invariance. Anyways, that's all I want to say. Thank you very much.